Okay, well, our last example that we're going to do in section 4.1, it talks about the absolute value function. So we're letting f of x be the absolute value of x, and the question is it differentiable at x equals 0? You probably remember the answer to that. Here's what the absolute value of x function looks like, basically. Well, it's just if you ignore it at 0, it is, well, it's certainly a continuous function. If you ignore 0, it would be differentiable. But at 0, we're going to find out that it's not. And you may remember an informal word that is sometimes used to be synonymous with differentiability. It's smooth. Smooth means no sharp corners. Well, we've got a sharp corner on the graph where x equals 0, and we'll show that it's not differentiable at that point. So I'll go ahead and write the answer, and now let's justify it. Let's consider a sequence. Sequence of xn's that converges to 0. The sequence xn is defined by xn equaling -1 raised to the n times 1 over n. And let's just take a look at what that sequence looks like. Notice that xn is equal to, I'm leaving off the n equal going to 1 to infinity. I should put that in. Is equal to what? Let's write out the first 4, 5, 6 terms. When n is a 1, this stays negative. Remember, when n changes, this is going to alternate from -1 to +1. When n is even, it's positive. So when n is a 1, it's going to be a -1 over times 1 over 1, so -1. When n is a 2, we're going to get 1/2. Back to an odd number for n, we're going to get -1/3, +1/4, -1/5, +1/6, and so on. So hopefully it's obvious that that sequence does converge to 0. The absolute value of these terms is getting closer and closer to 0. But let's consider the sequence f of xn minus f of 0 over xn minus 0. This sequence does not converge. Now we need to kind of explain why that's the case. If this doesn't converge, then it's not differentiable at 0. Indeed, for n even, we see the following. F of xn minus f of 0 over xn minus 0. I could have left that minus 0 off. That's equal to f of 1 over n. For n even, I can ignore the negative signs. For n even, xn's are just 1 over n. Minus f of 0 is just a 0. Over 1 minus n minus 0. So what we end up with is 1 over n. I'm going to leave off the minus 0 over 1 over n, which is equal to 1. That's okay. The limit exists of this. We took a subsequence, didn't we? We took all of the even-numbered terms. But for n odd, we see the following. F of xn minus f of 0 over xn minus 0 is equal to, this part will look similar, f of -1 over n minus f of 0 over 1 over n minus 0. Let's see, do that right. xn is 1 over n. This xn would be negative. So, because we're subtracting this value of x minus this value of x. So negative 1 over n. Okay, so n is odd, so we're going to get a negative 1 over n minus 0. But we're taking the absolute values. I didn't bother with the absolute values in the f of 1 over n because I knew they were all positive numbers. Over negative 1 over n, and this is going to give us a 1 over n over negative 1 over n, which is a negative 1. The limit exists, so what we have found, essentially we found two convergent subsequences. We found two convergent subsequences converging to two different numbers. That means that it's impossible that the sequence converges. So all we needed to do, let me finish this off. By theorem 1.4, f is not differentiable. I think 1.4 was the fact that if one sequence, the sequence we're talking about, this sequence right here, has two subsequences that converge to different numbers, then this is not a convergent sequence. We could also have simply shown that this sequence doesn't converge because the terms oscillate back and forth from 1 to negative 1. Instead, we chose to take the even terms, which converge to 1, and the odd terms, which converge to negative 1 in this sequence. So either way, the function f is not differentiable because this limit does not exist.